what is the one thing about elements that make them different, that make them distinguished? What's the one thing that we can use to identify an element? Number of protons. Good, the number of protons. Okay, so the number of protons that each atom contains is also called its atomic number. So the number of protons found within an atom is different for every single atom. Okay, so that's its one one quality that helps us identify the element, number of protons. So if I have an element that has 16 protons, tell me what element that is. 16 protons, what is it? Sulfur, right? It could have different numbers of neutrons, it could have different numbers of electrons, but if it has 16 protons, it's sulfur. If I remove a proton, do I have sulfur with just a -1 charge? No, what do I have? Phosphorus. Good. So if we remove that proton, it changes the element completely. So on the periodic table, it's usually listed in the top of the box. It's always a whole number because we can have parts of a proton, so the atomic number is always a whole number.
What's the Z?
Z is like the, sometimes you'll see it abbreviated. Atomic number is for some reason abbreviated with a Z. We'll never do that in our class, but sometimes in your book you might say, it might say find Z for this element, right? But we don't ever use that abbreviation, but some people do. Okay. Usually it's at the top. Atomic number is always a whole number because you can have parts of a proton. Okay, this number never changes for an element. Okay, so in a neutral atom, what's it mean to be neutral? No charge at all, right? So if in a neutral atom, the number of protons has to equal the number of electrons. So the atomic number can tell us the number of electrons in an atom as long as it's a neutral atom. If I have a neutral copper atom, how many electrons are found in that atom? 29. Good. Neutral means no charge, which means our positives have to equal our negatives. Okay, protons give off a positive charge, electrons give off a negative charge. Okay, very good. Atoms of any given element always have the same number of protons, right? So that means every hydrogen atom has 1 proton. Every oxygen atom has 8 protons. Every sulfur atom has 16 protons, right? We talked about the number of protons doesn't change. But there are some parts of our element that can change, and the identity of the element stays the same, okay? They can have different numbers of neutrons. So that means multiple atoms of the same element can have different masses. Anyone know what these are called? Okay. These are called isotopes. When we have atoms of the same element that have different masses, those are called isotopes. Okay. Atoms with differing numbers of neutrons that are the same element are called isotopes. So an example of this would be oxygen 16 and oxygen 15 and oxygen 14 or oxygen 17, right? These all might be versions of oxygen. Okay, and the number that's given out here is its atomic mass. Okay, how many protons does each of these versions of oxygen have? How many protons? Okay, look at your periodic table. How many protons of each of these oxygen atoms have? 8, right? They all have 8 protons. The only thing that's different is the number of neutrons. Okay? So that's really important. These are all isotopes of oxygen. What do we think the most common isotope of oxygen might be? Oxygen, 16. Why do we think that? The atomic mass given on the periodic table is closest to 16. That means that's its most common isotope. Okay? So we'll get into that here just a little bit more. But isotopes, atoms of the same element with different masses. Okay, so here's an example of hydrogen's isotopes. It has 3 stable isotopes. The first of which is regular hydrogen, right? That's by far the most common. 1 proton, no neutrons, 1 electron. Deuterium is the second one up here on the top right. Still has 1 proton, 1 electron, but it adds a neutron. Okay, so the number of protons is not changing. It's still hydrogen. This is called deuterium. The last one is called tritium. Okay, it's got 2 neutrons, 1 proton, 1 electron. Okay, so it's still a neutral atom. The only thing it's doing is getting heavier. Okay, these are all versions of hydrogen. Okay, they're isotopes of hydrogen. Okay. So the mass number, or the atomic mass, right? You can think of it in terms of atomic mass if you want. Is the total number of protons and neutrons in the nucleus of an element or of an isotope, right? Any isotope has all isotopes have a certain mass, and that makes it a certain version of each element. Okay, here's an example of what we would consider a nuclear symbol. You don't have to write all this part down. A nuclear symbol contains the chemical symbol, the mass number, and the atomic number. Okay, we said on the periodic table the atomic number is usually written at the top, but in the nuclear symbol it's flip-flopped. Okay, so in a nuclear symbol you would give the chemical symbol or the atomic symbol, mass, and the number. So you can just write down that as an example. We won't do a whole lot with nuclear symbols. Not anything you really need to worry about too much. Okay. So we're going to be able to calculate how many electrons, how many protons, and how many neutrons are in every element based just on a couple things in the periodic table. Okay, the atomic number tells us the number of protons and number of electrons, but what's the catch on this one? Number of electrons when? Good. Only in a neutral atom or neutral element, however you want to say that, in a neutral atom. Okay, so it doesn't tell us the number of electrons if our overall compound has a charge, right, or if our molecule has a charge, but it does tell us the number of protons and electrons as long as our atom is neutral. Okay? Sorry, we just talked about that. The mass number, or the atomic mass, right? I much more often use the term atomic mass, is protons plus neutrons. The important thing for us to remember is that the atomic mass is not the same for every single version of an element. Right? We saw hydrogens that have an atomic mass of 1, an atomic mass of 2, and an atomic mass of 3. Okay. So if I want to find the number of neutrons, I would take the atomic number, or the number of protons, away from the atomic mass. So I would say mass minus protons equals neutrons. Right? And atomic number is the same as protons. Okay, this should be review for us. Is that correct? Have we done this stuff before? Yeah? Okay, calculating protons, neutrons, and electrons. So this is how isotopes are usually written, with the symbol or the name and then a dash, and this means this is the atomic mass. Okay, so how many neutrons are in uranium-235? Okay, so how do we find out the number of neutrons in uranium-235? How would we go about doing that? Good. 235 minus the number of protons. We need to find uranium somewhere on our periodic table. Number 92. Good. It's just the symbol U. So what does 92 tell us? Number of 92 protons. So we're going to take 235 minus 92. And that means that in this isotope of uranium, we have 143 neutrons. Look at the mass of uranium that's given on your periodic table. What is it? What's the atomic mass of uranium given on your periodic table? 238. So that means that's another common version, right? 235 might be an isotope, but it might not be the most abundant if 238 is the average that's given on the periodic table. So if I was doing uranium 238, right, I'd say 238 minus 92. And on this version, I get 146 neutrons. Okay, both of which are uranium. They just have different numbers of neutrons, which means different atomic masses. Okay, so those would be considered isotopes of one another. Does that part make sense? Okay. Okay, now what happens if we have different numbers of electrons than protons? We have what?
Ions.
We have something called an ion. Very good. Okay, an ion is any charged particle. Okay, these are atoms with a positive or a negative charge. So if we have an uneven proton to electron kind of ratio or relationship, we have what we would consider an ion. Okay, anytime it's charged, we call it an ion. Okay, so an ion itself can be positive or negative. We're eventually going to dive into the different names for positive ions and negative ions, but not today. Okay, so if I have an atom that has more electrons than protons, does that mean I have a positive charge or a negative charge? A negative charge. Good. Very good. More electrons than protons, right? You just got to think of it in terms of that, right? I've got extra electrons, so it's going to take on a negative charge. If I have less electrons than protons, what type of a charge would I have? Positive, right? I'm short on electrons, so I have a positive charge. Very good. Okay, so for example, if I needed to write lithium with one less electron than protons. Okay, so let's think about that. Lithium itself is Li, and we know that it has one less electron. So does that mean it will have a positive charge or a negative charge?
Positive.
It's going to have a positive charge, and it's a positive charge of what value? 1, right? Because we're only one difference. So we just put up here a plus. Okay? We could put the 1, but usually whenever our charge is plus or minus 1, we just leave the 1 off completely. Okay? So really we would just say lithium plus. Anytime we have the 1, we can leave it off either way. Okay? Now if I have oxygen with 2 extra electrons, how do you think we would go about writing that? Its symbol with a... If I've got 2 more electrons, is it positive or negative? Negative, and I've got 2 of them that are extra, so it would be a negative 2. Charges are always written up, right, as a superscript. Okay, so like an exponent, similar to how you write an exponent, that's how you write the charge of something. Okay?
So if it's just like 1, you just put the plus or minus
Yeah, so if it was oxygen minus 1, we do just an O minus. If it's more or less, if it's more than 1, you got to put the actual number. Okay, questions there? All right. Okay, I don't want to do this part right now. Okay. So average atomic mass is exactly what you see on the periodic table. It's an average of all of the atomic masses from all isotopes of that particular element. Okay, so we know isotopes are the same element with different masses. You don't need to write that definition for the 5th time, but the average atomic mass is what you see on the periodic table. Okay, that's why most of them are decimal points, right? Most of them are decimal points because the average atomic mass is, it's a weighted average. So it takes into account how much of each isotope you get in a given sample. Okay, so for example, I want you to look at oxygen. What's oxygen's average atomic mass? 15.999, which is really close to what? 16. So what do you think oxygen's most common isotope is? 16, right? It's really, really close to 16. What do you think its next most common isotope would be? 17 or 15? 15, right? Because our average is 15.99. So that means an isotope of oxygen 15 pulls our average down just a little bit. Okay, does that part make sense? We're going to look at how we calculate our averages. So, and you look at an example of, let's say, magnesium. Magnesium is number 12. Look at magnesium's atomic mass. 24.3, right? So that means what is most likely its common isotope? Its most common isotope? 24, but what's probably its next most common? Right? 25. Or at least 26, right? Something bigger than 24, okay? They don't always necessarily go by ones, but we're assuming that its most commons are 24 and 25, right? But 24 has got to be more abundant since that's where our average lean towards. Does that kind of make sense? Okay. So this is a weighted average. So we're going to calculate a weighted average using this formula right underneath. Okay, and I'll break it down for you a little bit. Average atomic mass. This example uses 3 different isotopes, A, B, and C. We could use this same formula for as many isotopes as we have, right? Some maybe only have 2, some have 7, who knows, okay? But what we're going to do, we're going to take the percent of occurrence, which means like oxygen might be 99.9% of oxygen 16, and 0.1% of oxygen 15, right? We're going to take the percent occurrence times the mass of that isotope, plus the percent of the second occurrence times the mass of that isotope, plus the percent times the mass. Okay, we do that for as many times as we need to get through all of its stable isotopes. Something that we need to think about is when we multiply by a percentage. So if I have 99% times 16, right, do I really take it times a full 99? If it's a percent, what should I do? Do you know how to convert percents back to decimal places? Yeah, we divide by 100 or move it 2 to the left, so it would be 0.99. That would be the decimal place that we would use. Right? And then over here we might use 0.01. That would give us 1% of oxygen 15, right? If we were going about doing that, that's how we would do it, right? We can't use whole percentages. We want to put them back into its decimal form, okay, which you do that by dividing by 100. Okay, are we on the same page there? Okay. So this is just an example you can look at for copper, and I just want you to practice plugging this into your calculator, okay, and then we'll do one for real. But this is saying that 69.17% exists at 62.93 AMU, and 30.83% occurs at 64.93 AMU. Does that make sense where these numbers are coming from? right? This would be like isotope A, and this would be like isotope B. Okay, so this is just an example, and then we'll walk through one from the very start. Okay, 63.54. Look at the atomic mass for copper given on the periodic table. Right? Pretty dang close to what you just calculated. Right? So that means that copper is made up of two stable isotopes. One at 62, or about 63 really, and one at about 65. Does that make sense? So isotopes don't necessarily have to be in one AMU increments. These ones have two common isotopes, one at 63 and one at 65. So the weighted average for those puts us at 63. Okay, it leans more towards 63 than it does towards 65. Okay, are we on the same page here a little bit? Yeah. Okay. Let's try one together here. Okay. Find the average atomic mass of an element that has the following occurrences. So when we say occurrences, let's say I pull out a random sample of this element, and I'm able to analyze it down, and I find that 87% has this molar mass, or atomic mass. 10% has this atomic mass, and 3% has this atomic mass. That's where these numbers are coming from, right? 3% of any sample of this element would exist at this isotope. 10% would be this isotope, and 87% would be the other. Okay, so let's start plugging this into our equation. Good. Good. Okay. Any questions about finding average atomic mass? So whenever we look at the periodic table, we should be able to see essentially which is the most common isotope just based on which way our atomic mass leans, right? Like for nitrogen, we're at 14.007, which means nitrogen's most common isotope is probably what? 14. And what's its next most common isotope? Right? Probably 15 or 16 or something higher than 14. Does that make sense? So it won't necessarily go in one AMU increments, but it will be like the second one would be a little bit higher. Okay, so you should be able to see a really common, abundant isotope. The exceptions are like chlorine, copper, let's see some other that are like 0.5s. You know, that means they're pretty split evenly between two common isotopes. Does that make sense? Okay, very good.